It's worth taking a look back at some of the core basics of what voltage and current are, because they are most likely the most misunderstood parts of electricity. All matter consists of atoms. Atoms consist of two types of charge: negative electrons and positive protons. A substance which can conduct electricity does so because it has charges that are able to move. An electric current is a flow of charge. This current direction is referred to as the conventional current direction and is the one most commonly used. Conventional current flows from the positive terminal to the negative terminal of a battery. Unfortunately, this was decided before we discovered electrons, which actually move the other way. Depending on the source of the electricity, the current may flow in one direction only, that is, from positive to negative or vice versa. Or it may reverse its direction periodically, usually many times a second. A current which flows in one direction only is called a direct current, the symbol DC. A current which reverses its direction of flow periodically is called an alternating current, the symbol AC. The amount of moving charge is represented by the symbol Q. We measure the amount of charge in coulombs, or C. The strength of an electric current, the symbol capital I or small I, is measured in amperes, symbol A, using an ammeter. An ammeter is always connected in series. We calculate the current by this equation, where Q is the charge in coulombs, symbol C, I is the current strength in amperes, symbol A, and T is the time in seconds, symbol S. So the definition of current is the number of coulombs charge passing at a point per unit of time. An ammeter measures the flow of charge, the current. The ammeter is connected in series with the components of a circuit as it has very low resistance. Ammeters in series have equal readings, so ammeter 1 will equal to ammeter 2. Let's look at an example using this equation. A current of 0,5 amps flows in a circuit. How much charge passes through a point in the circuit in 2 minutes? Using the equation from earlier, we should remember that time must be in seconds, so to convert from minutes to seconds, we multiply by 60. This gets us to an answer of 60 coulombs of charge passing by in 2 minutes. The function of the power supply in an electric circuit is to replenish the electrical potential energy of the charges flowing through it. As the charges move around the circuit, their electrical potential energy is transformed into other types of energy in each component. All the charges then return to the power supply with zero potential energy. The charges function as energy carriers within the circuit. The potential energy gained by the charges as they pass through the power supply is lost to the circuit components, but the charges themselves continue around the circuit. This electrical potential difference, symbol V, is measured in volts, symbol V, also using a voltmeter connected in parallel across the ends of the circuit component. The potential difference between 2 points in a circuit is the work done per unit charge as the charges move from the one point to the other. Where V is the potential difference in volts, symbol V, W is the work done by the charges in joules, symbol J, and Q is the charge in coulomb, symbol C. One volt is the potential difference between 2 points in a conductor where 1 joule of work is required to transfer 1 coulomb of charge from one point to the other. Since work and energy are equivalent, the amount of work done by the charges is equal to the energy transferred to the circuit component before it is transformed into other types of energy, for example, heat and light energy. A voltmeter measures the potential difference across components of a circuit. The voltmeter is connected in parallel as it has a high resistance. Let's look at an example. A voltmeter is connected across a 9-volt battery. How much work is done by a charge of 6 millicoulombs passing through the battery? Remember, the charge must be in coulombs. M is milli, which is 10 to the minus 3. Substituting into the equation, we get 9 times 6 times 10 to the minus 3, which is equal to 5,4 to the minus 2 joules. If we place batteries in series, we add to get the total potential difference. If we place batteries in parallel, the potential difference is the same. This means that there's more energy stored and it'll take longer before the energy runs out.